In section 3.3, we look at our third and final definition of the trigonometric functions. And here we call them the circular functions. Same thing. First, let's talk about the unit circle. So the unit circle is a circle where the center is at the origin and the radius is equal to 1 unit. The equation of the unit circle is x squared plus y squared is equal to 1. And you can see that it consists of all of these points right here. And the four most important points on the unit circle are the points 1, 0, and then we also have the point 0, 1, the point -1, 0, and the point 0, -1. Now let's talk about how the trigonometric functions relate to this unit circle. So here we have our unit circle, and within this circle we are going to draw an angle theta such that the terminal side of this angle theta in standard position intersects the unit circle at some point x, y. So xy is a point on the terminal side of theta, and we know the distance from the origin to this point xy, this distance has to be 1 unit, since the radius is 1. And then if you make the corresponding right triangle that goes with this angle, this will be x and this will be y. And again, the hypotenuse here is 1. And we can actually think about the old definition for sine and cosine. So we know that cosine of theta is x divided by r, but since we're on the unit circle, r is 1, so it's just x divided by 1, which is x. Likewise, sine of theta is y divided by r, but again, r is 1, and so y divided by 1 is y. So what we have here is when you have a point on the terminal side of an angle theta on the unit circle, the sine and cosine of that angle are given by the coordinates y and x respectively. So if I'm looking at an angle theta and I want to know what is the cosine of theta, it's just the x coordinate of the point of intersection on the unit circle. And sine of theta is just the y coordinate of the point on the unit circle. So here we have the official definition of these circular functions. Little different picture. So on the previous page, we had an angle theta in standard position like this. And the point xy is the point on the terminal side of theta, also on the unit circle. And we talked about how cosine was x and sine was y. Now what I'm doing is I'm saying, well, if theta is an angle in standard position, the measure of the angle theta in radians is s divided by r. We know the radius of the circle is 1, and s is the arc length. Well, in this picture, the arc length is the length here, and they are calling that arc length t. So the measure of the angle theta in radians is t divided by 1, which is t. So for all intents and purposes, when we say the angle theta in standard position, that's the same thing as saying t, where t is the length of the arc intersected by that angle. Okay? So let's go back to that definition now. If xy is any point on the unit circle and t is the distance from the point 1, 0 to the point xy along the circumference of the circle, then we have the following relationships. The cosine of t equals x, sine of t equals y. Tangent of t? Well, tangent is y divided by x because, remember, tangent is always sine divided by cosine. Cotangent is the reciprocal of tangent, therefore must be x over y. Cosecant is the reciprocal of sine, so it must be 1 over y. And secant is the reciprocal of cosine, so it must be 1 over x. And now I want to show you the unit circle with special angles. So here we have the unit circle, which is the circle centered at the origin, radius equal to 1 unit. And I have superimposed all of the special angles on this unit circle. So for example, here is the angle 30 degrees, which is equivalent to pi over 6 radians. Here is the angle 45 degrees, which is equivalent to pi over 4 radians, etc. And then I have the corresponding points on the unit circle for all of those special angles all the way around. Now we'll talk about these points in just a second here, but I want you to notice that the numbers you see in the first quadrant are the same numbers that you see in all 3 quadrants, except for the fact that some of the numbers are negative and some are positive, and that just depends on whether x and y are positive or negative in those respective quadrants. So if we're on the unit circle at an angle of 30 degrees, how do we know the point is radical 3 over 2, 1/2? Let me show you that. Let's look at the corresponding triangle here. So if I draw the corresponding right triangle for 30 degrees, it will look like this. And if I pull that out, here is what that triangle looks like. We know the hypotenuse of this triangle is 1, right? Because the hypotenuse, notice, coincides with the radius of the circle, and we know that the radius is 1. If this is 30 degrees, we need to remember that in a 30, 60, 90 triangle, the shorter leg is half of the hypotenuse. So if the hypotenuse is 1, the shorter leg is 1/2, and the longer leg is radical 3 times the short leg. So it's radical 3 times 1/2, which is radical 3 over 2. So now you can see the length of this side is radical 3 over 2. Well, that's the x-coordinate of this point. And the length of this side is 1/2. That's the y-coordinate of that point. And so that's how we get these numbers radical 3 over 2, comma 1/2. It just comes from the relationships that we know in a 30, 60, 90 triangle. Now, of course, at 60 degrees, that same triangle is just rotated, right? So now the short leg is x and the long leg is y, and that's why the 2 coordinates that you see here are reversed for 60 degrees. And then, of course, at 45 degrees, we can also draw a triangle. So at 45 degrees, we have this right triangle. Again, we know that this is 45 degrees. We know the hypotenuse coincides with the radius here, which is equal to 1 unit. And we know in a 45, 45, 90 triangle, the leg is the hypotenuse divided by radical 2, and the legs are the same. So that's where 1 over radical 2 and 1 over radical 2 come from. Now, when you get into the other quadrants, for example, at 3 pi over 4, the reference angle for 3 pi over 4 is 45 degrees. So that means the sine and cosine are going to be the same values, 1 over radical 2. However, in the second quadrant, cosine is negative and sine is positive, right? And remember, cosine is the x-coordinate and sine is the y-coordinate. So you don't have to memorize this unit circle, but it's a great reference as you're doing problems. But keep in mind that you need to be able to figure out sines and cosines of special angles without looking at this picture. Let's do some examples. So in our first example, it says to use figure 4 to find the 6 trigonometric functions of the angle 5 pi over 6. So if I'm looking at the unit circle, the first thing I want to do is locate 5 pi over 6. So it is this angle here, right? Also the same as 150 degrees. And I want to get these 6 trigonometric functions of that angle. So that means we want to get the sine of 5 pi over 6, the cosine of 5 pi over 6, tangent, 5 pi over 6, cotangent, right, etc., secant, and cosecant. All right, well, to do this, we need to know the definition on the unit circle. So on the unit circle, sine is the y-coordinate of the point of intersection. Cosine is the x-coordinate. Tangent is y divided by x. And then the rest we can get by reciprocals. Cotangent is x divided by y. Secant is 1 over x. And cosecant is 1 over y. So what I need to do is identify what is x and what is y for this angle 5 pi over 6. And you can get that just by looking at the point that corresponds to that angle. So the x-coordinate of that point is negative radical 3 over 2. The y-coordinate of that point is 1/2. So once I identify that x is negative radical 3 over 2 and y is 1/2, then all I have to do is simply plug those values in here. So sine is y, which is 1/2. Cosine is x, which is negative radical 3 over 2. Tangent, I need to do y divided by x. And this is going to be 1/2 multiplied by the reciprocal here. And that ends up being negative 1 over radical 3. Cotangent is the reciprocal of tangent. So if tangent is negative 1 over radical 3, cotangent is going to be negative radical 3 over 1, which is negative radical 3. Secant is the reciprocal of cosine. The reciprocal of negative radical 3 over 2 is negative 2 over radical 3. And finally, cosecant is the reciprocal of sine, and the reciprocal of 1/2 is 2. So if I have a picture of this unit circle available, finding trig functions of special angles is relatively easy. Now let's look at a slightly different problem. It says to use the unit circle to find all values of theta between 0 degrees and 360 degrees for which cosine of theta is equal to 1/2. Now remember, cosine of theta on the unit circle is the x-coordinate of the point. So if we say cosine of theta equals 1/2, what we're saying is x has to be 1/2. So to find all the angles theta for which this is true, I only need to look at the points on the unit circle and find all the points where the x-coordinate of that point is 1/2. And that occurs right here at 60 degrees, and it also occurs down here at 300 degrees. No other point on the unit circle has an x-coordinate of 1/2. So the angles theta for which cosine equals 1/2 is going to be 60 degrees or 300 degrees. And if they had asked for these angles in radians, we would simply say theta is pi over 3 or 5 pi over 3, right? Because you can see the radian equivalence of those angles here. Now let's talk about even and odd functions. This is an algebraic concept. The definition of an even function is a function for which f of negative x is the same as f of positive x for all x in the domain of the function. So a quick example from algebra of an even function is think of the function f of x equals x squared, right? If I do f of negative x, according to the definition of this function, that means to take negative x and square it. And when you square negative x, that's negative x times negative x. The negatives here cancel out, and you get x times x, which is x squared. And x squared is the original function f of x. So what you can see is when you do f of negative x, essentially the negative you plug in gets absorbed and goes away. So f of negative x is the same as f of x for all x. Now, if you look at the graph of f of x equals x squared, the graph is a parabola which looks something like this. And there is a geometric meaning to when a function is an even function. So here is a positive value x, and when you plug that into the function, you get a corresponding y value there. And what you should notice is that when you plug in negative x, the opposite of x, you are getting the same y value. And that's because when you have an even function, you have symmetry across the y-axis. All right. Now let's talk about what it means to be an odd function. The definition of an odd function is a function for which f of negative x is equal to negative f of x for all x in the domain. So a quick example of an odd function would be the function f of x is equal to x cubed. So if I do f of negative x for this function, it means to take negative x and raise it to the third power. And if we do that, we get negative x times negative x times negative x. Now, two of these negatives cancel out, but we still have a negative left over. And so what we have here is negative x times x, which is x cubed. And since x cubed was our original function, what we have here is negative f of x. So x cubed is a perfect example of an odd function. Now, what does that mean in terms of a graph? Well, let's graph f of x equals x cubed. And I am assuming that we sort of remember how to graph x cubed. It looks something like this. And the idea is as follows. When you plug in a positive value for x, you get a particular y value. And when you plug in the opposite of that value of x, you can see that you get the opposite y value. So what I mean here is if y is 5, for example, then down here it's going to be at negative 5. What's happening here is if you draw a line from one point to the other, it goes through the origin. And so odd functions have this trait of having symmetry through the origin. And we'll talk more about what the symmetry means later on when we start graphing trig functions. So what does this mean for the trigonometric functions? Well, here we have our unit circle. We have our point xy on the terminal side of some angle theta. And then we have the point x negative y on the terminal side of negative theta. Now, why is this point x negative y? Well, you can see that if you have the same reference angle in the first and fourth quadrants, they are going to have the same x value here So the x-coordinate of this point and the x-coordinate of this point are the same. However, the y-coordinate here is positive and the y-coordinate here is negative, but it's the same distance. So the y-coordinate for theta we call y, and the y-coordinate for negative theta we call negative y. But we also know that x and y on the unit circle are equal to cosine of theta and sine of theta respectively, right? We know cosine of theta is x, and we know sine of theta is y. And for negative theta, it's the same thing. Cosine of negative theta is the x-coordinate. Sine of negative theta is the y-coordinate. So what do we get from this? Well, cosine of theta here is x, and cosine of negative theta is also x. So cosine of negative theta and cosine of theta are equal to each other. This means that cosine is an even function, right? Because what we're saying is f of negative x, or let me say it this way, f of negative theta is the same as f of theta. And then for sine, it's the opposite. Sine of negative theta is negative y, but sine of theta was positive y. So sine of negative theta is negative sine of theta. So what we're saying there is f of negative theta is negative f of theta. And this means that sine is an odd function. So what you need to remember from this is cosine is even and sine is odd. So to put this more succinctly, cosine is even, and what that means is cosine of negative theta is the same as cosine of theta, and sine is odd. And what that means is sine of negative theta is negative sine of theta. Now let's take a look at a couple of examples. So in this next example, it says, show that cosecant is an odd function. And I am going to summarize which trig functions are even and which trig functions are odd in just a minute. But how do we show that cosecant is an odd function? Well, we start by saying cosecant of negative theta would be equal to what? What do we know? Well, we know no matter what, cosecant of any angle is the reciprocal of sine of that same angle. So cosecant of negative theta is 1 over sine of negative theta. And then we have to ask ourselves, well, what do we know about sine of negative theta? Well, what we know is that sine of negative theta is negative sine of theta, because sine is an odd function. That's what we just showed on the previous page. So 1 over sine of negative theta is the same as 1 over negative sine of theta. And I could pull that negative out in front of the fraction, which is going to give us negative 1 over sine of theta. And then we know that 1 over sine is cosecant. So this is equal to negative cosecant of theta. So what I have here, if you take the beginning and the end, is I have cosecant of negative theta is the same as negative cosecant of theta. Therefore, cosecant is odd. So let's talk about a quick summary before we do this next example. All trig functions are either odd or even. The even functions are cosine and its reciprocal, which is secant. The odd functions are the rest. So sine is odd, cosecant is odd, tangent is odd, and cotangent is odd. So the way I remember it is to remember cosine is even. That's what you have to remember. Cosine is even. Therefore, its reciprocal is also even. and the rest are odd. Okay, let's go back to this example now. So I want to use the fact that the trig functions are either even or odd to get the following values. So first one, sine of negative 60 degrees. Well, the sine of negative 60 degrees is the same as negative sine of 60 degrees. And this is because sine is an odd function. So when you have an odd function, it's kind of like the negative gets factored out, okay? And then we can complete this by saying this is negative radical 3 over 2, because we know the sine of 60 is radical 3 over 2. For our next example, we have cosine of negative 2 pi over 3. Well, cosine is even. When you have an even function, the negative gets absorbed. So the cosine of negative 2 pi over 3 is the same as cosine of 2 pi over 3. Now, what is the cosine of 2 pi over 3? Well, we have to change 2 pi over 3 into degrees at this point, or we have to go to the unit circle. I'm going to do it the old-fashioned way. 2 pi over 3 is 120 degrees. And then 120 degrees has a reference angle of 60 degrees. However, 120 degrees is in the second quadrant, and cosine is negative in the second quadrant. So this is negative cosine of 60 degrees, which is negative, what? 1/2, right? Now, another way that I could have done this is I could have just simply gone to the unit circle. Let me bring it up here real quick. So here's our unit circle. Once I established that cosine of negative 2 pi over 3 is the same as cosine of 2 pi over 3, all I have to do at that point is find the angle 2 pi over 3, which is right here. And then all I got to do is look at the x value of the point. And that x value is negative 1/2, right? So the unit circle makes finding trig functions of special angles really quite simple and pleasant. But I caution you all to not rely too much on the unit circle, because you may not have it all the time. Some instructors don't allow unit circles to be used on exams and etc. So you need to remember how to do these values kind of the old-fashioned way, using stuff that we learned before this section. One more example here, we have the secant of negative 225 degrees. So secant of negative 225 degrees, secant is even, so that is the same as the secant of positive 225 degrees. And then all I would need to do is, once again, look at that unit circle to find this value. And if you look at the unit circle, you will see that this value is negative radical 2, right? And the way you get that is you do negative 1 over the x coordinate, which is, you do positive 1 over the x coordinate, which is negative 1 over radical 2, okay? So that's from the unit circle, which I don't have on this page, okay? But how would you do it if you didn't have the unit circle? So again, what I do is I say, well, secant of 225 is 1 over cosine of 225, right? And then 225 has a reference angle of 45 degrees. And 225 is in quadrant 3, and cosine is negative in quadrant 3. So what I have is negative 1 over the cosine of 45 degrees. Now, the cosine of 45 degrees, that's one of those values that we should have memorized. So we have negative 1 over radical 2, and that ends up being negative radical 2. Okay, so again, if you have the unit circle, it's relatively simple to find these values. If not, you have to kind of do it, the old-fashioned way.